What I want to do today is I want to talk a little bit about Green's theorem. Okay. And so Green's theorem is one of the gems of multivariable calculus. It's got several different close cousins. There's the Stokes theorem, there's the divergence theorem. How many of you are considering a career in physics? If you continue in physics, especially if you do electricity and magnetism, you will be using these all the time. How many of you are considering a career in pure math? All right, so if you're going to do pure math, eventually if you do complex analysis, you will see an analog of Green's theorem. So it's worth seeing this. It's a result that's useful. It's a result that's a natural generalization of something you've seen before. This will not be on the exam. This is just to give you a sense of what's out there. There is a difference between Math141 and Math150. 150 does sequences, series, Taylor series, and all the like. 151 does Green's theorem and stuff like that. And so I want to spend at least one day quickly going over what they are. So you've at least seen it. It's on your radar screen. But I do not want to test you on it. I do not want to give you problems on it. I just want you to be aware that it exists and it's useful. If any of you are thinking about your future classes, I'm always happy to chat. I think there's a lot of advantages in being a math stats major, taking a lot of classes in the department. You're just getting a sense of how do you think about problems. And so a lot of the topics for the last 2 weeks of the semester is going to just be what's out there, what will you see in your next classes, or how does a mathematician think about problems. And so we'll be doing a little bit more of that next week. All right, so I'm going to just state this. I went to Wikipedia. I debated not using it because they use the letters L and M. Most books use P and Q, but it doesn't really matter. But I do cringe a little bit, seeing the L and the M rather than P and Q. So what it says basically, imagine you have a nice curve. And it turns out it's a little bit hard to define precisely what we mean by a nice curve, but roughly it doesn't cross itself and it splits the plane into two parts, which we name interior and exterior. And I think you should be able to tell which is which. And so we travel the curve counterclockwise. We always do things counterclockwise. That's how we travel. So your region is on the left as you walk. It doesn't matter, but since everybody uses this notation, it just makes it a lot easier. And then what it says is a certain line integral, L dx plus M dy. The way you should view that is we have some function f of xy, which I'll write as L xy m xy. So I'm going to write it as a vector. And then I have my vector ds, which is dx dy. And then f dotted with ds is going to be L dx plus m dy. Another way, if you want to view this, is you could have your curve, c of t, which is going to be x of t, y of t. And then we would have f of c of t dotted with c prime of t dt. And that's what we would integrate. And when you look at what is c prime of t, that's going to be essentially L dx m dy related with the dt's. So this is how you would really do those integrals. We would have some kind of curve. If it's a circle, maybe we would have cosine t sine t. If it was an ellipse, maybe it would be 2 cosine t, 3 sine t, something like that. And then how do we evaluate? It's f of c of t dotted with c prime of t. If I have two vectors and I dot them, what do I get? I get a number. Okay, now we'll give me a number as I go around. And what Green's theorem says is that if you look at this line integral, so this is essentially the integral over my curve c of f of c of t dotted with c prime of t dt, that's basically equal to the curl of f dx dy over the region. We have to be a little bit careful. So it's been a while since we've seen, the gradient and the curl operators and whatnot. Technically, the gradient of f, so technically the curl of f is a vector. But since we're working in the plane, we're just forgetting about the z component. the whole point of this theorem is it says a one-dimensional integral. And that's really what we have when we look at it as a function of t, integrating along the curve. It's a one-dimensional integral. This is equal to a two-dimensional integral. Okay. Do you think it would ever be advantageous to go from a one-dimensional integral to a two-dimensional integral? Can you come up with a choice of m and l where it might be easier to do a two-dimensional integral? What would be a particularly nice value for dm dx minus dl dy? Imagine I'm a nice guy, and I wanted to give you the easiest possible function to do a double integral. What would dm dx minus dl dy equal? Nope. I could be even nicer. 0. Right? If I give you 0, what is the integral of 0 over the region D? It's 0. If I give you the function 1, I'm actually being nice. But you would then have to know what is the area of D, and that could be a hard calculation. So imagine you have a function whose curl dm dx minus dl dy is 0. Oh, okay, well, then I can just do that area integral immediately. I get 0, so I know the line integral is 0. Why is this useful? The line integral could often represent the work done by a force. And so in physics, when you're trying to figure out how much work has been done or how much work would be needed to move something, you want to actually evaluate integrals of forces acting on particles along paths. And so sometimes it could be easy to extend. Okay. I'm just throwing in here a snippet of some calculations I did, not surprisingly, in Mathematica. So I chose my first function f of x, y to be x over x squared plus y squared to the 3/2, y over x squared plus y squared to the 3/2. Does anybody know what that function is? So it's written in a way that might be a little hard to follow. What should be your first thought when you see x squared plus y squared? Convert to polar. So the denominator would become essentially r squared to the 3/2, which becomes r cubed. So this is going to be, r cosine theta over r cubed. So it's going to be cosine theta over r squared, sine theta over r squared. Does anybody know what kind of force that would be? Object. Now here's my source. This would be a repulsive force, where the force is pushing you out in the direction of the radius. Because if I'm at the point x, y, notice that the direction of f is the same as the direction of x, y. I've just rescaled it by a factor of 1 over r to the 3/2. There's 1 over r cubed. 1 over r cubed. So do you agree that f is in the same direction as the point x, y? Because they have the same denominator, just pull that out. So f is in the same direction as your point. So this would be equivalent to I'm pushing my particle away. What force from physics might this be? Where I have a radial force that's pushing away. I'm sorry? What's the trick? There's one of the standard ones you should see, one of the fundamental rules. I'm sorry? No, I'm thinking of a physical force. I'm sorry? Well, so does a magnet, so you could do magnets. Is it going to be 1 over r squared force? There's one that I know is 1 over r squared force that's related to magnets. Not springs. Electricity and magnetism, if you have two charges that are the same, they repel. Two charges that are opposite attract. So gravity is a attractive force. It attracts proportional to 1 over r squared and in the direction that connects them. So here, if I had, say, 2 positive charges, then they would be repelling. And the force would be like a 1 over r squared force. And so I just did the calculation, what is, the derivative of the second component with respect to y minus the derivative of the first component with respect to x. Mathematica has a command that does that. And it calculates it and the answer is 0. It really should be a vector, but because we're living in the plane, it's just forgetting about the other components. Yes?
Mathematica, is that the dominant sort of engine?
For a lot of, yes and no, I'm not going to answer this with the recording going on. I will happily talk about that after class. I'll just briefly say Mathematica is wonderful for many calculations, but it is not open source. So you have to trust that the algorithms, you don't necessarily know how things are being calculated. A lot of people use programs like Sage and other environments where it is open source. And if you want to see, so how is it calculating the determinant? How is it calculating the eigenvalues? You can see what it's doing. And there's a real split in the math community about, what should you be using? For standard stuff like this, absolutely fine to use something like this. So the second one is I chose the function g of x, y. It's a vector valued function. Its first component is negative y. Its second component is x. So its curl is 2. So if you think about this, why would I choose that? Well, the curl, the derivative of the second component with respect to x minus the derivative of the first component with respect to y. So if that equals 2, what would this integral be? What would the area integral be if dm dx minus dl dy equals 2? So if dm dx minus dl dy equals 2, what would that area integral be? You'd be integrating 2 dx dy. So what would you get if you integrate 2 dx dy over the region D? What would you get? So let's calculate. I want to integrate over the region D the function 2 dx dy. That's just 2, the integral over d of dx dy. What do you get if you integrate the function 1 over the region D? Sorry, not d close to d.
D squared.
Not d squared. D is a region. So maybe here's my region D. What do I get if I integrate the function 1 over the region D? You're making it too complicated. Think simple. So give me a region. Somebody give me a nice region.
Square.
Okay, square. So take a square of side length 5. Integrate the function 1 over a square that's 5 by 5. What would you get? 25. Give me another region that's nice. Circle. So take a circle of radius 5. Integrate the function 1 over a circle of radius 5. What would you get? 25 pi. Take the function 1 and integrate over the region D. What would you get?
The area.
The area of
D.
of D. So this is just twice the area of D. Now, if D is a tough region, I don't necessarily know what the area of D is. The whole point of Greenspan is if I choose this wonderful function, wait a minute, I can go from this 2-dimensional integral to this 1-dimensional integral. I can calculate areas by doing line integrals. And so if I can do the 1-dimensional integral, if I can do the f of c of t dot of c prime of t, I can now calculate areas of certain regions. So this becomes a very interesting way to find areas. So this is another application of Green's theorem. I'm not going to say too much about Stokes' theorem. This is just, the slides are here. It's a generalization of Green's theorem to higher dimensions. And what it does now is it replaces an integral over the boundary of the region. Say I have, I should have brought it. think I still have it from when I was a graduate student. I took a plastic bag and I taped it to a coat hanger. So the coat hanger becomes the boundary, and then the plastic bag is the surface. And it reduces integrating over the surface to integrating just along the coat hanger. And no matter how you change the surface, the boundary is the same. So all of these integrals are still the same. I'll try to remember to bring that to class on Monday if I can still find it after all these moves. And then the last one, and again, we're not going to talk too much about these, just to know that they exist, is instead of doing del cross, you could do del dot, which is df dx plus df dy plus df dz, and that's going to be related to a volume integral related to a surface. So all of these integrals are taking something from one dimension and relating it to something of a higher dimension. And the general one is completely unintelligible form is the integral of d omega over omega is the integral of the pullback or the inclusion, I guess the inclusion of omega over d omega. So let's unwind what that is. So fundamental theorem of calculus. If I integrate over the integral AB f prime, what do I get? This is the integral over AB above df. What would I get? So you integrate f prime, big F prime. What's the integral of big F prime? Sorry? Say that again? No, we're integrating big F prime. Big F, right? What's the integral of big F prime? I undo the derivative. If I have big F prime and I integrate, I get back big F. I'm integrating over AB, so what will the answer be? Big F of B minus big F of A, which is big F evaluated at AB. And what we can really do is, if you want, I'm going to write it like this, where this means boundary. And so one way to view the fundamental theorem of calculus is if I integrate the derivative of a function over a segment, that's the same as essentially the function evaluated over the boundary. What's the only closed curve you can have on the real line, where you start and stop at the same point? Just a point. So what would the integral from A to A of f prime equal? 0. The technical condition or statement is boring. Right? If I integrate over a closed curve in the line, well, if I walk forward and then I walk backwards, walking backwards cancels the walking forward, and it's effectively the same as integrating over a plane. So the only closed curves in one dimension are a point, and integrating a function over a point is boring. But in two-dimensional space, in three-dimensional space, you can now have non-trivial closed curves where you start and stop at the same point, but you travel some path to get there. So it turns out that you can generalize the fundamental theorem of calculus. And we typically do it over some kind of closed region. We have to be a little bit careful because of one dimension. You really don't want to call this the fundamental theorem of calculus. It's just too straightforward. The integral of any function over a point is 0. Not too exciting. But when you're stepping into higher dimensions, integrating along a curve, and this is essentially what's going on. This is why things are related to different dimensions. The derivative is over the higher dimensional thing. And then the antiderivative is over the lower dimensional. So in one dimension, we would have the derivative of big F over an interval that is related to the antiderivative big F over the boundary of the interval, and so on and so on. Okay. If you have done any physics, you might have seen Maxwell's laws and all of these different laws. What comes into play frequently relations involving d by dx, d by dy, d by dz. That's the gradient operator. they come in as del cross or del dot. And again, this is not a physics class. This is not going to be on any of the tests, but it's just nice to know roughly what's out there and what might you use a little bit more, physics orientation for multivariable calculus. Where would this stuff provides? That's what I want to do. Is I want to start doing Green's theorem. So I'm going to use P and Q because that's how I was taught. So I want the integral over some curve, gamma P dx plus Q dy is equal to the integral over the region R, dq dx minus dp dy dx dy. So this is Green's theorem. All right. I need a simple shape to start doing my calculation. Can somebody think of a nice shape for me to do the integral of? Square. It could be a little bit more general than a square.
Right.
Rectangle. Right. What is the other possible candidate? An ellipse or a circle, which is a special case. Right. The problem is ellipses and circles don't fit together nicely, but rectangles do. And so the hope is if we can prove the result over a rectangle, we can prove the result in general. So let's take a rectangle. And let's do this as the point A, comma, C. This would be B, comma, C. This would be B, comma, D. And this would be A, comma, D. And we travel like this, and I'll call this gamma 1, gamma 2, gamma 3, gamma 4. So I'm going to go through my region, and I'm going to show that the integral of p dx plus q dy equals the double integral of dq dx minus dp dy. No, not. I'm going to show half of it. I'll show one of the terms on the left equals one of the terms on the right, and I'll just wave the pen and say, and if you argue similarly, you can show the other ones the same. So if you look at gamma 1, we're going from the point AC to the point BC. I claim either dx or dy is very easy to understand as you go along the curve gamma 1. Which is the one that's easy to understand, dx or dy? Why? Good. What is dy? So dy equals 0. And so it's up here, dy equals 0. What about on gamma 2? Which one is easy to understand? Yeah, there's no change in x, so dx is 0. Okay. So we've got some idea of what's going on. So if I want to integrate p over gamma, so I want to integrate over the closed curve gamma of p. I should really be viewing this as the integral of p of c of t dotted with c prime of t dt. This is how I really unwind this. But I claim I'm sorry, I can't do p. P comma q. So I'll let f of c of t be p of c of t q of c of t. I've got to remember I've got to have a vector. And I'll get f of c of t dotted with c prime of t dt. So that's going to be the integral of p is going to be the integral of, if I take f dotted with c of t, I'll get p of c of t dotted with x prime of t dt. This should really be, it shouldn't be f. Should be the integral. And similarly, the integral over gamma of q would be the integral of q of c of t dotted with y prime of t dt. And dx dt dt, that's really just our dx. And dy, dt, dt, that's really just dy. And that's why this integral is really just the integral of f dx plus q dy. Again, I'm just trying to give you enough of a sense that you can see that when you put everything in, this is reasonable as to where Greenspan is coming from. I just want you to be aware of the existence of this theorem. Should we see it? You should not be at the point where you're going to do problems on this, but just have some idea of what is p dx plus q dy. Well, the way we do things is we have a vector valued function. So f is going to be p comma q. And then the way we do these line integrals is I take the dot product of it with c prime of t dt. And c prime is going to just be the vector x prime comma y prime. So I'll get, my p dx and I'll get my q dy. And so we see we've got the p dx. There's really no dx on gamma 2 and gamma 4. So my integral over gamma of p dx is just going to be the integral over gamma 1 of p dx plus the integral over gamma 3 of p dx. And I have to remember the orientation I have for those. Okay. Now, restoring the picture. So I want to look at the area integrals now. I have some idea of what the left-hand side is. Let's look at the right-hand side. Do you want to do the integral of dq dx or the integral of negative dp dy? dq dx. So let's do the double integral of dq dx, dx dy. Do you want to integrate with respect to x first or with respect to y first? X. And if I gave you, the integral of dp dy, would you rather integrate with respect to x or y first? Why? Why do we want to do them in this order? Well, what function has derivative dq dx with respect to x? I'm sorry? Q. Is that the only function that works? There's others. But they all differ by constants, right? And their constants will depend only on y. They can't depend on x. So if I think about what's going on, okay, so I'm doing the x integral first. So x goes from a to b, y goes from c to d. So this would be the integral, y goes from c to d, and then I have what function has derivative q? It would be q of x comma y at a and b dy. If you want, we could do it more generally. It would be q of xy plus some function that depends only on y. And I evaluate this at a and b. But what's going to happen to that function h of y when I evaluate it at x equals a and x equals b? Nothing, it's going to cancel. I have h of y at b, I have h of y at a. So whatever that constant is, it doesn't really matter. So because it doesn't really matter, I can drop it, or I can just say it doesn't matter. So this is just going to be the integral y goes from c to d. And I'll get q of b y minus q of a y dy. Okay. So this is the same as the integral y goes from c to d of q of by dy plus the integral y goes from d to c of q of ay dy. Why is this true? Did I drop the minus sign? I switched the order. So instead of going from C to D, I'm now going from D to C. Why would I do this? Well, if I look at the first one, y goes from C to D and x equals b. That's just the integral of q over gamma 2. So I get the integral over gamma 2 of q dy. And the second one, because I'm going from D to C, that's going in the right direction for gamma 4 of q dy. This is almost the integral of q dy over the entire curve gamma. I'm just missing the integral of q dy over gamma 1 and the integral of q dy over gamma 3. What's the integral of q dy over gamma 1? It's 0. Why? Because dy is not changing. So this is then the same as the integral over gamma of q dy. As the integral of q over gamma 1 equals the integral of q over gamma 3 is 0. So this shows you that the integral of q dy is equal to the integral over the region of dq dx. So a very similar argument will show you that the integral of p dx is equal to the double integral of negative dp dx. And so this is Green's theorem. And so if we have a rectangle, we now have the result. And so the main concern we have is if I give you a region like this, what I want to do is I want to chop up the region. I'm deliberately staying away from the boundary right now, just to start. I have something like this. Okay. Does everyone agree that I can chop it up like this? I've got to worry about what happens as I get near the boundary, but when I'm well in the interior, I'm going to just have a bunch of rectangles that fit together beautifully, right? And now let's think about what's going on. Let's consider a couple of these rectangles. So I'm going to zoom in a little bit. And so now, on this rectangle, I go around the line integral counterclockwise. And on the one below, I go around counterclockwise. How much time do I have to fill up? 13 minutes. It's on.
Turn down the clock.
I'll stop. What do you notice going on? Yeah. Not quite integrating by parts. Yes. Yeah, all the interior sides cancel. And so for these 4 squares, it becomes the same as just it just expands out like that. All the interior stuff cancels. And so if you look at the line integrals, your Green's theorem tells me the line integral of p dx plus q dy equals the area integral. Well, all the different area integrals will just add together. And you'll just be integrating, the curl over the whole region. And all the interior stuff would cancel. If I didn't have, oops, if I didn't have the square over here, So if I get rid of that square over there, if I were to keep playing this game, what would happen, I'll go back to my game. Is it would now look like this. So all the interior segments would cancel and it would just push out to the boundary. So as I keep doing this, it's going to get closer and closer and closer to integrating over the boundary. So this is where you now have to start doing things very carefully. So if I give you, a region like this, we want to break it up. So what if instead I gave you something like this, maybe. Dot, dot, dot. If I took a polygonal approximation, then that should be really close. The area integral should be almost the same. The amount that I'm going to miss by is very small. This is what you have to do to keep things similar. If I do a polygonal approximation like this, then in the limit, the area integral is going to converge. But what about the line integral? Does the line integral converge as you go along these polygonal paths? And you have to be a little bit careful here. Did we prove in this class that all curves have the same length? All right, I'll prove to you that all curves have the same length. Can somebody give me a curve connecting these two? Okay, so I could do a parabola. Parabola coming up like this. Okay. Well, what I can do is I can approximate this parabola by polygonal Gaussian path. How much time do I have to fill in? Right. Do you agree that this is a really good approximation? And that for each part of the curve, I'm going to just replace it with a polygonal. Right? And so do you agree that a really good approximation for the length of the curve is just the length of the polygonal path? And that as I take a finer and finer mesh, a la Riemann sums, it should converge to the length of the curve, correct? What would happen if we dropped all the horizontal paths down? What would that give us? Okay, so we drop all the horizontal down, we get a straight line like this. What would happen if we drop all the vertical lines to the right? What would we get? So what we've just shown is that any curve that's strictly increasing, its length is just equal to the horizontal distance plus the vertical distance. Well, I know at least one curve where that's bullshit. What's the one curve where that has to be wrong? Straight line, a la Pythagoras. If I take this, we know it's false in that case. What's going on? If we zoom in, here's one of my segments. And this all comes down to the size of relative error. If I look at how small of an error I'm making, am I making a large error on an absolute scale if I replace the length of the curved line with the two red lines? No. But is my relative error large? Absolutely. Locally, the big point of Calc 1 is that locally every curve is a straight line. And so locally, what it should be is, if ds is the length of this, and this is dx and dy, its ds should be like the square root of dx squared plus dy squared. Or if you want, delta s should be like the square root of delta x squared plus delta y squared. We did ds is dx plus dy, or delta s is delta x plus delta y. So that's the problem, is that if we want to approximate those small little segments, if I want to do something like the length, I can't just say it's the sum of the two polygonal pieces. Right? I need to have, it's the square root of the sum of the squares. Is the square root of the sum of the squares just the sum of the elements? Is the square root of a squared plus b squared a plus b? No, so you consider 3 squared plus 4 squared, that's 5, but this is not equal to 3 plus 4. This is a simple proof that the square root of a sum of squares is not. And so you have to be extremely careful when you do calculations like this, because we can't just say the lengths converge. We're not doing lengths, we're doing line integrals, we're doing dot products and whatnot. And when you put all this in, you can show that everything converges. But you have to do some work here. The other thing that's often done in problems like this is you want to have your functions where things are differentiable. So for gravity, is there a place where you might have trouble using 1 over r squared for your force? Where might be a very bad point to place the object you care about? Yeah, if you put it basically right in the source of your force, there is no r, it's going to blow up, right? So we can't talk about differentiability at this point. It's not even defined. So in order to be differentiable, you have to be continuous. So as soon as I know I'm not continuous, I know I'm not differentiable. So when I try to use things like Greenspan and Stokes theorem and whatnot, it often comes down to, well, I need my function to be defined on a region. So what we would frequently do, this is a wonderful idea, is let's say you have one point where it blows up. And you have a curve that is fine everywhere else, but you have one point where it blows up. So what you would do is you're coming around, you're coming around, you're coming around, and then what you do is you come down like this, and you go in a small curve around it, and you come back up. So for that segment, you've gone down it, and then you come back up. What does it do? If you come down and then you go back up, what does it do? It cancels out. And so what you can often do is you can say the integral along this boundary curve on the outside is the same as integrating along a small circle centered at the point where it blows up. And so if you call this c sub epsilon for circle of radius epsilon, you call this gamma, you would often get the integral over gamma of your function is the integral over c sub epsilon of your function. Being vague in terms of writing what's going on. When you big picture, if you continue in mathematics, this is what often happens. And in a beautiful subject called complex analysis, you often reduce integration to just finding the negative first Taylor series coefficient. So if you look at the Taylor series and you calculate, okay, I've got so many x squared, so many x, except we use z because it's complex, so many z squared, so many z, so many ones, so many z to the minus 1. It's the coefficient of z to the minus 1 that matters. The z to the minus 2, z to the minus 3 doesn't matter. You can reduce a lot of very difficult integrals to just integrating along the circles. And what you can frequently do is, let's say you want to integrate over the real line. What you can do is you can extend the integral by adding extra segments. And if the integral over those 3 segments tends to 0, as you go over a larger region, not drawn to scale, plus r from 0, minus r, minus r. So if you let big R go to infinity, you can often show that the integral over those 3 sides don't matter. And then it all comes down to just what goes on at one point. So if I give you the integral of 1 over 1 plus x squared dx, does anybody remember what function has derivative 1 over 1 plus x squared? It's arctangent. And so this is just arctangent at infinity minus arctangent at minus infinity. Arctangent at infinity is going to be pi halves. So this is pi halves minus negative pi halves, so you get pi. 1 over 1 plus x squared, where does that blow up? Where does 1 over 1 plus x squared blow up? Yes. X equals I or negative I. So it turns out you can use complex analysis and figure this out. Now, we don't have to do this because we remembered the trig substitution. But what if I gave you the integral from minus infinity to infinity of 1 over 1 plus x to the 4th dx? Good luck trying to do this one. It's perfectly fine on the real axis. It turns out that it has a couple of places where it blows up in the complex plane. And you can reduce integrals like this to very easy ones. So this is just a beginning of where all of this goes. And there's a lot of wonderful things that you can do with this. It's incredibly powerful. It takes a while. You have to try a lot of things. When you're learning a new subject to see what will work. We've gone through this when we're integrating. We have all these different techniques. We try, and hopefully one of them will finally do the problem and solve it. This is a new powerful way to integrate. It's one of the most powerful ways we know. It's very strange. The way I do a one-dimensional integral is I extend it into a complex integral. But anyways, this is meant to just give you a little bit of a sense of what comes next. If you're doing physics, if you're doing electricity, magnetism, you will see Green's theorem and all this stuff when you get to these equations. If you continue in mathematics, complex analysis eventually deep down the road is a wonderful place for stuff like this. All right, so this is all I wanted to do on Green's theorem. This will not be on the exams.